Alright guys, let's sharpen your engineering skills even more because today I will explain how and why it's possible to achieve a similar thrust by cutting the propeller diameter in half. Of course, if you simply interchange the props, you'll get the result you expect. The bigger one performs better. Then comes what I call the efficiency bonuses. The duct, the stator, and the nozzle. Those plastic parts don't add thrust by themselves. They help transform more of the propeller available power into useful thrust. A lot of energy is wasted with the single open prop, so the design goal is clear: reduce the losses. The propeller creates a pressure difference across its blades, and that pressure difference is what generates thrust. But with an open prop, high pressure water can leak around the blade tips and escape sideways. That's wasted energy. The duct fixes this, and it should be as close to the prop diameter as possible. You still need a functional clearance so nothing rubs, but minimizing the gap is critical. This prevents water from escaping around the tips and reduces tip vortices, since high pressure water can't easily leak to the low pressure side. And now that we have a duct, the propeller configuration matters even more. The blade should cover as much of the duct cross section as possible. This helps build higher pressure downstream, which becomes useful later. In my case, adding an extra blade might even help. The next bonus feature is the stator. As you can see, it has 5 slightly curved blades. Their job is to straighten the flow. After the propeller, water is not only moving backward, it's also rotating and turbulent, which doesn't contribute efficiently to thrust. The stator removes swirl, reduces turbulence, and converts wasted rotational energy into more usable pressure and cleaner actual flow. The last bonus is the nozzle. Right after the propeller, there is a temporary pressure buildup. Without the nozzle, this pressure is almost instantly released into surrounding water. The nozzle allows us to use this pressure efficiently. Under Bernoulli's principle, pressure can be converted into velocity. The faster we expel water backwards, the harder we might expect to be pushed forward. But now, how do we dimension a nozzle correctly? In this case, size matters. The nozzle principle is simple. The same mass of water per second must enter and exit the system. If the exit area is smaller, the water must leave faster. That's the continuity idea. What goes in must comes out. If the nozzle is too small, pressure builds excessively and the system begins to choke. If the nozzle is too short, the pressure release is abrupt and energy is wasted outside. If it's too long, or losses increase and the flow becomes inefficient.